Hello, YouTube. It's Taylor again. Boy, it sure has been a while. I just moved up to Pacifica from Los Gatos, and moving took a lot of my time, so I stopped producing YouTube videos for a while. But what I did not stop doing was I did not stop working on rover projects. So I'm going to tell you what I've been working on, and I've got screencast going on my desktop, so I'm going to give you a little bit of overview. Obviously, you've seen you've seen this footage before, but I'm going to talk about the software projects I've been working on, including and in particular the reinforcement learning project I'm working on so that I can create a camera-based vision system for Rover. So if you're familiar with these videos with Rover, you know that I've created a four-wheel drive open source robot that has articulated suspension. It's all 3D printed. It's a CC0, no copyright, open source. You can do anything you want with it. And I'm really interested in open source robotics that can do useful work. And so you see that Rover here is a very capable vehicle, but all of these shots are remote control. Here's a nice shot of the gearbox, and in case you didn't realize it, you see in this picture, Rover is 800 millimeters long. It takes up more than half of the trunk in my SUV. It's a big robot. So the reason why I made it so big is so that you can mount serious compute and sensor hardware on it so that you could actually make it totally autonomous and have lots of room for software development. So Rover is an open source software development platform for robotics, and in particular I'm very interested in vision, camera-based vision systems. So then the question is, how do you create a camera-based vision system? And I am very interested in the intersection of machine learning, which is fantastic at processing image data, and robotics navigation systems. So typically on a robot, you are going to have sensors that have a very high quality understanding of the world. You're going to put that into a 3D model of the world, and you're going to plan a path based on this 3D model, and everything is computed in a very algorithmic, there's sort of a traditional kind of algorithmic computation that happens in robotics that doesn't use machine learning. Machine learning is a little different, and it's something that I'm extremely interested in getting more experience in, and so I've got my first big machine learning project is to start with something that I think is a simple tractable problem, and that is make it so that Rover can use a camera to follow a trail, like a hiking trail. I want to do this because it would be really fun to have a robot go hiking with me on a trail. That would be really fun. It's also a narrow enough problem that I have some confidence that I could solve it. NVIDIA has already published their own neural network they call TrailNet that helps a drone follow a trail, and that's really cool. I didn't quite like the approach that NVIDIA used, though, and instead I found this research. So I'll describe it in a moment. So it's called World Models. This page is worldmodels.github.io, it's the let's see here. So the authors are David Ha from Google Brain and Jürgen Schmidhuber, who's just a classic an AI researcher. He's been in AI for decades. And I highly recommend reading this paper. It is an extremely approachable, readable paper. And they present a model for doing two different things. They show how the same architecture can be used to dodge fireballs in the video game Doom, and also to steer a race car on a track. And so what's going on is that the network is getting pixels, and the pixels are the same pixels that you're seeing right here on the screen that the car is driving on. And then it has control for the car. So this is just like if you were playing a video game, you're looking at the screen and you've got left, right, gas, brake. So the neural network learns how to, look at the screen and figure out how to steer this car. And when I look at this, I say, that looks a lot like following a trail. And in fact, because they also used it to dodge fireballs in Doom, which was a very different environment, I have some confidence that if you were to put a camera on Rover and point it at a trail, if you were somehow able to train the whole system to digest those scenes, it seems like this system would work. In particular, I'll explain the system as a very high level, but the world model's architecture is basically 3 different neural nets that work together. So the first is the variational autoencoder. This takes an image of the scene, and then it uses magic, convolutional neural nets, and it converts it into the latent vector z, which is a 32 number array. So it takes a 64 by 64 pixel image and turns that into 32 numbers. So it's a highly compressed representation of the scene. And this is trained by going through the encoder into that latent vector and then decoding it again and training it based on how well the output looks like the input. What's really nice about that is that 64 by 64 pixels is a lot of data, and you turn that into just 32 numbers. That's a smaller piece of data, but it still represents the scene. As you can see on here on the reconstructed frame, this came from only those 32 numbers, and the decoder was able to figure out what the actual scene looked like with enough precision that you'd still be able to dodge that fireball. And then the next thing is the recursive neural network. So the latent vector z from the variational autoencoder is a compressed representation of the scene as it's being seen in each time step. That latent vector is fed into the recursive neural network, and the recursive neural network's job is to sort of keep track of time series data, and in this case it's used to predict the next image frame. And so it learns what the next image frame looks like given the current image frame. And then that is all fed into the controller model. So the controller model is a fully connected net that receives both the latent vector from the variational autoencoder as well as the output of the recursive neural net, which is a prediction of the next image. And so the controller model has the current image and the next image in compressed form, and then it is trained to figure out how to steer the vehicle. And the breakthrough of this paper is that because a lot of the heavy lifting is done by other pieces, the recursive neural net, which has straightforward training, and the variational autoencoder, which has straightforward training, the controller doesn't have as much work to do. It can be smaller, and training a fully connected net is typically difficult. So the fact that it's smaller means it becomes tractable, and it works well in this case. It works so well that this was the first model to solve the OpenAI gym environment called car racing, which is what you're looking at right now. So if I go to the OpenAI page, they have this task, car racing v0, and you can see here that's the thing. The source code's on GitHub there. But basically they put all these challenges. If we click on environments for a minute, my internet's pretty slow, but here we go. You can see they have Atari-based environments, a lot of Atari-based environments. There's some other control-based environments, some robotics-based environments, etc. And this is one of those environments, and they have a leaderboard, and anybody is welcome to submit a score that they've gotten on this. So the world models got the best score, and it looks like a really great place to start for trail following. Great. Okay, so I've selected this as research that I want to reproduce in my first foray into machine learning so that I can give Rover the ability to follow trails autonomously. Great. So how am I going to do that? Well, there's a physics simulator called PyBullet, and that is a great place to start. I played around with it a little bit, and I had some trouble with that at first, although I did go back to it. But between the first foray and now, I also tried using Unreal Engine. And Unreal Engine has a Linux-based editor. They give you the source code, although it's not open source, but they share the source. You're not allowed to reshare it. And you compile it yourself on Linux. And there's a plugin called Unreal CV that lets you pull frames out of the video game and do computer vision on that or whatever you'd like. And so Unreal CV looked like a great way to hook up Unreal Engine to the OpenAI gym environment, which is a reinforcement learning environment that basically lets you take an observation and then step the world and then take another observation. So I created a video game, in Unreal Engine that is another simple continuous control task from pixels. This is showing the high-res version. I made a 64 by 64 pixel version. Oop, there we go. I got 301 points, but I fell off. And if I hit R, then it resets. And if I hit P, then it unpauses. I can also step through it. So if I hit S, and so the stepping interface is the interface that I gave to the OpenAI Gym environment. I had a lot of problems with Unreal Engine. For example, this game, which is a cube on a plane sliding past a bunch of other rectangular prisms, you'd think that's a pretty simple game. This executable is 750 megabytes. It's just really heavy. That's not in itself a problem, but it's indicative of how heavyweight this solution is. In fact, compiling Unreal Engine was a pain in the ass, and when I then tried to compile Unreal CV against Unreal Engine, I found that Unreal CV was only compatible with certain versions of Unreal Engine, and I had to, using trial and error, roll back Unreal Engine and then recompile it, and then try to compile Unreal CV against it, until finally I found a version of Unreal Engine that worked with Unreal CV. Finally got that working, and was still unable to step the environment faster than real time. And so it meant that collecting data was very slow. I also had an issue where the screenshot function of Unreal CV didn't work, and so I had to use a different screenshot method, which was very slow. I had to add, a couple hundred milliseconds of delay around this just to make sure that it worked, and I tried backing that off and had problems. And so I was able to train oh, I've lost, the game has captured my mouse. So what I was able to do was I downloaded somebody else's implementation of the world models paper, where they had a really easy 1, 2, 3, 4, 5 step process for training with your own gym environment. So I turned the Unreal CV, or the Unreal Engine video game, into an OpenAI gym environment, and then I ran it through somebody else's code that would do the training. And I did succeed, sort of, in training the variational autoencoder. What you see here is I made random latent vectors, that z vector. I made random z vectors and decoded them just to see what the VAE would be seeing. And so these are, the imagined output of the VAE, and it kind of works. I'd like to wrap up this section talking about Unreal CV, but let me say, or Unreal Engine, but I found basically that the training was happening, but there were so many problems with Unreal Engine. I would have needed a much larger data set. Collecting that was a problem. And it was all very heavyweight. It was all very slow. When it came to the final training step, there were some other problems, and I finally just decided I needed to take a break from that. So I backed off from Unreal Engine and worked on some other stuff for a while. Finally came back to this project, and I started looking at procedural generation. This blog post was pretty inspiring for me. So this individual talks about how he procedurally generated these mountainous environments and how he made realistic looking trails on those environments. And he talks about the algorithm and makes sure that instead of having some trail that just goes straight up your mountain, you have a trail that has a more realistic looking height increase as it goes up the trail. So I saw this is a procedurally generated world, and I said, okay, the other Unreal Engine game, and by the way, that was not a trail. I was starting with something I thought would be simpler. I think the world models would train and be able to steer that cube left and right to avoid the obstacles. It was going to be worth a shot. I really wanted to get used to Unreal Engine, and it wouldn't have been too hard to change the game to be a car and a trail later, but I didn't quite like that. So went to using procedural generation, and I'll show you a little bit what I've got so far. So this is still in progress, but I wrote some Python code that generates an OBJ of a kind of a nice little curvy world here, and I'm just still playing with the actual path generation algorithm. You can see here the path is intersecting with itself. I need to enforce something there. Oh, excuse me. But you can see here I have a simulated four-wheel drive robot, And if you look here, you can see that there's the first person view. So there's a virtual camera on that robot. So I did all of this in the Bullet physics engine. PyBullet specifically is what I'm using. So this is all Python code. It's really nice. And look, you can see it's almost going to make it to the trail. Yep, didn't quite make it this time. Right now, it's just rolling forward continuously with no input. But this physics engine is made expressly for, well, PyBullet is used a lot for machine learning. It's very well suited for it. And this is all much lighter weight. This whole thing is a couple of K of code to generate these worlds. Less than that, probably. And this is procedurally generated, so it could be generated. It starts with a random number, and it just generates a world based on that. And what I'm going to do is I'm going to put the virtual rover on this trail. Woo, hello. Yeah, it's running a little less than real time. It's a little slow still. And so that's why it looks like it's in space and the gravity is wrong. It's just that physics is running a little less in real time. But I have much more confidence in using the Bullet physics engine to be able to do this training. And so I would like to at least train the robot to be able to drive down a virtual trail. Now, there's something called transfer learning, which is when you train in simulation and then you try to get the thing to work in the real world. And it's not easy. And if I train on a cartoonish world like this and then go put Rover out in the real world and run that network on the vehicle, it's not going to work. It's absolutely not going to work. So I need a little bit of special sauce. And that is what I've got right here. So if you take a look at this, this is a 3D capture of a trail. You see, unfortunately, a gap in this capture right now. But this is a 3D capture of a trail, and I generated this by taking video with my cell phone, and then using a process called photogrammetry, I was able to convert the trail, the video. I took 3 frames per second out of the video, took a folder of images, I set up a Google Cloud Compute instance with some software called OpenSFM, which stands for Open Structure for Motion, and then another piece of software, OpenMVS, which is Open Motion View Stereo. And those 2 pieces of software, they both have great tutorials, and I basically just did what their tutorials tell you. You do the OpenSFM tutorial, and then you export to OpenMVS, and then you take that exported file, and then you do what OpenMVS would say to do in their tutorial. It's all pretty straightforward. And what you get out is a textured mesh. So if you see here, I think there might be some compression artifacting on my viewer, but you can see that this is not just a point cloud, it's actually a mesh of lines, and that might be a nice view there as well. So this is a virtual trail environment, and I can actually put this in the PyBullet physics simulator, and I can drive the robot around on it. But that's not the only capture I have. Here's another one. So this is a nice long trail. And if we try to zoom in a little bit, here we go. You can see that, yeah, so this is this is a nice trail. I can put this in the physics simulator also. There are some issues. I'm still kind of working out the approach here. I'm worried about the fact that if you have a vehicle on here, it's going to see the edges, and that's going to be pretty disorienting for it. So that's a little weird, but let's see what else do we have. This was a fun photogrammetry capture. It's not a trail, but I did a capture inside a building. And all these can be loaded into the physics simulator. So we could have the robot, a virtual robot, drive through this building a little bit. And it could get a feel. You could tell it to drive straight down that hallway, and it could get a feel for what that looks like. Let's see, what else do we have? This one is still in progress. I took video walking down the trail, and then I turned around and came back. And when I turned around and came back, the capture didn't align properly. So some parts of it look good, but there's other parts that you see here. This is messed up. The trail does not look like that. It's flat. So the process has some some issues. Let's see what else. Oh yeah, this is one of my favorite captures. This is a trail in Lake Tahoe. I went an offsite with friends, and they went climbing, and while they were climbing up a rocky face, I went and recorded video for photogrammetry purposes. So this is a nice virtual trail environment. One thing I've noticed is that there's a lot of data sets for indoor buildings because all the researchers in the world work indoors. And the whole reason why I'm making an off-road robot is that I want to get outdoors. And so there's not a lot of outdoor data sets. And so I'm going to share all this. This is all going to be open source, totally unrestricted. I'm going to put these OBJ files on GitHub, and y'all can play with them. But this one's kind of this one's pretty cool. You see, there's a lot of artifacts, and it's going to be interesting to see if those artifacts actually mess up the network and make it so it doesn't transfer, or if the artifacts are just another peculiarity of the world that this thing learns to handle. And let's see, oh, this one's missing its texture. I'm not sure. Oh yeah, that was I showed you the other one. It didn't load properly. That's this one. It didn't load properly in that software for one reason or another. These files are all a little bit different. But yeah, so just to recap now, we can finish up here. I have built a four-wheel drive robot, and I want to learn how to use cameras and neural networks to make a functioning vision system. I've chosen a narrow tractable task, which is that I would like this robot to be able to follow a trail. This is going to be the beginning of me learning about vision systems for robotics, so that using machine learning, so that I can begin to get comfortable with it, and from there I can expand it to being able to navigate a network of trails or more. I'm using the world models research along with OpenAI Gym and the PyBullet physics simulator, and I am slowly trying to train my robot to be able to drive along at first a virtual trail and hopefully someday a real trail in the real world. So this is all that I've been up to. Actually, I've been up to more lately. There's some gearbox design work that's been going on behind the scenes, so trying to robustify Rover's gearboxes, but I have been doing a little bit more of the software projects lately. I'll do another update with more information. I want to wrap this up, but thank you so much for listening. Please, if you think this is what I'm working on is cool, then please visit the website reboot.love, create an account, and say what you thought was interesting. Also, definitely like and subscribe the YouTube channel. So this is my personal YouTube channel. This is what I do just because I think it's really critical that we make open source hardware for our robotics in addition to open source software. And I'm trying to make that be a thing. So if you thought this was interesting, give me a thumbs up, like, subscribe, share with your friends, go to a party, tell everybody about it, or just check back again next time. So thank you so much, and I hope you have a wonderful rest of your day.